Check this out. We've got something really fun today. This is so amazing. Oh man, again? 8.1 Logarithms. Let's start off by graphing y equals 10 to the power of x, and let's graph y equals log x. Now in your calculator, this is the default log, so if you just press log x, that will give you a base of 10. What do you notice? This is y equals 10 to the power of x, so it looks like an exponential and it has a horizontal asymptote here. This is y equals log of x. And what do you notice? Looks like this one is a reflection of this one in the line y equals x. Now, if it's a reflection in the line y equals x, what does that mean? Since they're reflected in the line y equals x, they are the inverse of each other. So if we have y equals 10 to the power of x, the inverse is x equals 10 to the power of y. Now, to get the y out of the exponent position, we've had to invent the logarithm function. And you got to memorize where each of these pieces go. The exponent gets freed up, and now it's all by itself on the other side. The base of the exponent becomes what is called the base of the log. And what was over here, our answer, becomes the argument of the logarithm function. So that's our input for this function. So log can't exist by itself without an argument here, just like sine, cos, and tan can't exist without an angle or a theta in its argument position. Exponential form is an expression or function written with an exponent, and logarithmic form is when it's written with a log function in it. The default base of the log is 10, and so we don't need to write it. Just like the index of a square root is 2, but we don't write it because that's the default base. So you'll find log on your calculator, and it means log base 10. The other commonly used base is base e, which creates the natural logarithm, so we write ln. We don't use this in 30-1, but we do use it in calculus, and IB uses it a lot. And so you'll see this button on your calculator, the natural log of x, and it just means that the base is e, which is a constant something like pi, an irrational constant. First, we need to know how to go from exponential form to log form, or from log form to exponential form. And you just have to memorize where the 3 bits of information go. The base of the exponent becomes the base of the log. The exponent gets freed up here, and whatever it equaled becomes the argument of the log. Let's try this one, rewrite into log form. So we have the exponent here is x minus 1, so it gets freed up and put by itself on one side. Then we'll have log, and the base of the log is going to be the base of the exponent, so this base will be 4. And then what was on this side here becomes the argument of the log. And in this case, that's all the question wanted us to do, just rewrite it in log form. Let's try this one. This one's in logarithmic form. Now let's write it into exponential form. So we have the base of the log was the base of our exponent. Now this was the exponent that got freed up here, so I need to put it up here in the exponent position. And this would be wrong if I left it like this, because we need brackets to show that that exponent applies to both the 4 and the x. The argument of the log is what this exponential expression here was equal to. And there's the same thing, just rewritten into exponential form. What exactly does the log function do? Well, it was invented by a Scottish mathematician, John Napier. He realized that we needed a function that will get the exponent out of the exponent position. It's helpful to think about the log function as answering this question. What exponent does the base need to equal the argument. So for this example here, what exponent does 10 need to equal 100? Well, it needs an exponent of 2. It sometimes is easier to see this when it's rewritten in exponential form. So if we take this expression, put the 10 back as the base, put the x back as the exponent, and this argument of the log function is on the other side of the equation, we can see that this is indeed what the question is asking. 10 to what exponent is equal to 100? And sometimes it's easier to do it that way. Let's evaluate these logs without a calculator. So 7 to what exponent gives me 49? Well, 7 squared is 49. What 6 to what exponent gives me 1? Well, 6 to the power of 0 gives me 1. And get to this question, it might be a bit more difficult to see. This one is 10. 10 to what exponent gives me this decimal? Well, it's definitely a negative number because this is smaller than 10. But this one might be useful if we rewrote it into exponential form. So let's do it. The base here is 10. We want to find the answer, and we'll call it x here. And this equals the argument, so 0.001. Let's rewrite this into a fraction. It probably will be easier to see. So 10 to the x is equal to 1 over 1,000. Now we can see that 10 to the power of negative 3 would give us 1 over 1,000. So this would be negative 3. What about this next one? This next one you may want to rewrite into exponential form too, but it's possible without. 2 to the power of 3 will give me 8. And if I wanted a square root, that would just be over 2. So let's try to rewrite this in exponential form. So 2 to the power of x, there's the answer that I want, is equal to 8, the square root of 8. And I'm just going to write the square root of 8 as 8 to the power of 1/2. Remember, the index of the radical becomes the denominator of the exponent. Now, I'm going to rewrite 8 as a base of 2. So 2 to the power of 3 gives me 8, and just the 1/2 is still there. And then these two exponents I multiply together. So 2 to the power of x equals 2 to the power of 3 over 2. And you can see that x must equal 3 over 2 because the bases are the same. Let's try this next one. 9 to what exponent gives me 81? Well, 9 squared gives me 81, and then the base of this, the index of this becomes the base of our exponent, so 5. What about this one? This one's a bit messier because there's two parts to this log argument. So let's say 3 to the power of x is equal to 9 root 3. Now 9 can be written as 3 squared, and root 3 can be written as 3 to the power of 1/2. Now we add these exponents because they have their own bases. So 3 to the power of x is equal to 3 to the power of 2.5. Now we see that x, the answer that we were looking for, is 2.5. Or you can write 5 over 2 if you prefer a fraction. For these ones, we want to find the value of x. So we'll rewrite them in exponential form. Here's the base, 5, and here's the exponent, negative 3. And that equals the argument of the log, which is x. So in this question, x is equal to 1 over 5 cubed, which is 125. The next one here, we've got the base is x and the exponent is 2, and that's going to equal 36. Now we're going to square root both sides here, and normally we would get plus or minus x, but in 30-1 we only want the positive answer because we want the base of the log to only be positive. So we'll say that x is equal to 6. For this one, same thing, 64 to the power of 2/3 equals x. And you probably want to do the cubed root first, unless you're using a calculator. The cubed root of 64 is 4, and then 4 squared is 16. So x is equal to 16. Next one, 4 is the base, negative 2 is the exponent, and that equals x. So x is equal to 1 over 16. Next one, 16 to the power of negative 1/4 is equal to x. So that means that x is equal to 1/2. And last one, x to the power of 2/3 equals 9. And this one, let's do some algebra. Let's multiply, or let's raise each side to the power of 3 over 2. Each side to the power of 3 over 2, which is taking the square root of each side and then cubing each side. That will get rid of these exponents. So we get that x is equal to 27. Graph the inverse of f of x without a calculator. Since I'm not allowed to use a calculator, first I'm going to sketch f of x on this graph. Now that I've sketched f of x on the graph, I know that the inverse will be reflected in the line y equals x, or I can also use this table of values that I made, and the inverse will be switching the x and the y values of each coordinate. So now I'll do that, and I'll draw the inverse on this graph. So the inverse of f of x is drawn in blue here. I took every point here, such as negative 2, 4, and I swapped those two values, so I got 4, negative 2. Then I plotted it on the graph. Make sure to exaggerate the space in between your functions and the axes. Even though on your calculator it would look as if it touches, we don't want it to look like that when we sketch it. There's an invariant point here where x equals y. And notice that f of x had a horizontal asymptote, and the inverse has a vertical asymptote. The Richter scale assigns a magnitude to an earthquake, and it uses a base 10 logarithmic scale, where the magnitude, m here, is the log base 10 of the amplitude of this earthquake divided by an arbitrary minor amplitude, which we'll call A0 here. An earthquake has an amplitude of 10 to the power of 5.4 times A0. What is the magnitude? So our magnitude is m, so that's what we're trying to find. We've got our log base 10 here. We know that the amplitude of this earthquake is 10 to the 5.4 times A0, so that's the amplitude of this earthquake, and we have it divided by A0 here. Remember, this is all inside the log function. We see that A0 and A0 will cancel, and I'm left with the magnitude is equal to the log of 10 to the power of 5.4. Now, this log is easy to do without a calculator because this base is 10 and this is also base 10. So 10 to what exponent gives me 10 to the exponent 5.4? Well, it's just 5.4. So that would be a magnitude earthquake of 5.4. If the magnitude of an earthquake is 8.1 on the Richter scale, pretty intense earthquake, how many more times intense is it than A0? So here's the magnitude of 8.1. And this time, you need to find how many more times intense is it. So let's find this A value here. So let's rewrite this into exponential form. So the base of this log is 10, so that will be the base of our exponent. This is our exponent, and this is A over A0. Now, to solve for A, we just need to multiply both sides by A0, and that actually gives us that A is 10 to the 8.1 times A0. Now, the question says, how many more times intense is it than A0? And here it's set up as this many times more intense than A0. So we actually just need to figure out what this is. So 10 to the power of 8.1 is equal to 125 million 892,541 times more intense than A naught. How many more times intense is a 9.5 magnitude earthquake than a 6.5 magnitude earthquake? Let's just do this a quick way. We know that 6.5 to 7.5 is 10 times more intense because that's how this base 10 scale works. We know that to 8.5 from 7.5 it's 10 more times intense, and to get to 9.5 it's times 10 again. So to get from 6.5 to 9.5 it's 10 times 10 times 10, or 1,000 times more intense. Last one. What magnitude earthquake is 4,984 times more intense than a magnitude 3 earthquake? First, let's find what the amplitude of a magnitude 3 earthquake is. So that would be 3 is equal to the log of A over A naught. And we get that this 10 to the power of 3 is equal to A over A naught. And that means the amplitude is 10 to the power of 3 times A naught. Notice we don't know what A naught is. That's okay. We just bring it with it. Next, we need the new amplitude and new magnitude. So to find the new amplitude, we just need this amplitude and multiply by this. So that would be 10 to the power of 3 times A naught times 4,984. The new magnitude, then we'll say, is M new, and that is going to be equal to the log of all of this new amplitude divided by A naught. And you can see that the A naughts cancel, so nowhere in this question did we need to know it. Sometimes they give you that value, sometimes they don't. And our new magnitude then is just put log 10 to the power of 3 times this in your calculator, and you get about 6.7. This was part of Relations and Functions 7 and 9, understanding logarithms and graphing logarithms. Hopefully you can do all of these things. Here's some questions. Try them out. See if you know what you're doing.